This is motion in 2 and 3 dimensions, and we'll be paying attention to these modules. Module 4.3, average acceleration and instantaneous acceleration. Module 4.4, projectile motion. Module 4.5, uniform circular motion. Module 4.7, relative motion in 2 dimensions. Okay, we can get started. A proton initially has velocity of 4.0 I minus 2.0 J plus 3.0 J, and then 4 seconds later, it has velocity minus 2.0 I minus 2.0 J plus 5K in meters per second for that 4 seconds. What are A, the proton's average acceleration, averages in initial vector notation, B, the magnitude of the average acceleration, and C, the angle between the average acceleration in the positive direction of the x-axis. So the average acceleration is going to equal V final minus V initial over T final minus T initial. So V final is going to be minus 2.0 I hat minus 2.0 J hat plus 5.0 K hat, and we got to subtract a minus 4.0 I hat plus 2.0 J hat minus 3.0 K hat, and this is all over 4 seconds. And this is going to go to, we got a minus 2 I and a minus 4 I, which gives us a minus 6 I hat. We got a minus 2J and a plus 2J, which gives us a plus 0J hat. And we got a minus 3K and a plus 5K, which will give us a plus 2K hat. And all this is divided by 4 seconds. And what this is going to lead to is a minus 1.5 I hat and a plus 0.5 J hat. So that's A. And for B, they want the magnitude. So the magnitude of A, average, is just going to be the square root of the minus 1.5 I hat squared plus 0.5 J hat squared, which is going to equal 1.6 meters per second squared. This is meters per second squared acceleration. And finally, the angle between the average and the positive direction. So the angle between the average, so we'll just go theta equals 10 to the minus 1 of J, which is 0.5, divided by I, which is a minus 1.5, and that's going to equal a minus 18.43 degrees. And we're going to plot this. The minus 1.5 I hat. And this point here is a 0.05 J hat. And we get this triangle, which is 18.43 degrees is here. And then to read it from here to here, you're going to have 180 minus 18.4. And that's going to give us, this angle is 161.6 degrees. Now we're going to work some problems in 4.3 of Holiday and Rexnert, Chapter 4 on projectile motions. Problem 2.2, Chapter 4. A small ball rolls horizontally off the edge of a table that is 1.2 meters high. It strikes the floor at a point 1.52 meters horizontal from the table's edge. How long is the ball in the air? What is speed at the instant it leaves the table? So we're going to draw a table. And the ball is going to roll off it. The table is 1.20 meters high. So it strikes the floor at a distance of 1.52 meters. Rolls off, strikes the floor. So we need to get some time, and also we need to get V sub O, which is going to be the initial velocity. We know since it rolled off the table horizontally, there's no Y component when it first rolled off. A Y component once it began to go in this parabolic motion. So first, let's get the time. So we know that the table is 1.20 meters high, and we could go with this formula here. Y equals Y sub O plus V sub O sine theta times T minus 1/2 G T squared. And we can solve this. We know that Y sub O is going to be 1.2 meters. We know V sub O sine of 0 degrees, that's equal to 0. Then we have our minus 1/2 GT squared. And we also know when it hits the floor, it's at 0. So now we can solve. This Y represents when it's right here, when the ball is on the floor. So that's 0. So what we have is minus 1/2 g t squared equals minus 1.2 meters. And this is going to go to, since we've worked this, t equals the square root of 2y over g. So we have that will equal 2 times 1.2 divided by 9.8, and that equals, so t is equal to 0.49, and we'll just round this up to 5 seconds. So now that I know that, I can use x equals v sub o times the cosine theta times t to get v sub o. We know cosine of theta is 0 degrees, and the cosine of 0 degrees is 1. So we can just say this goes to v sub o equals, we know what x is. X is this distance here, which is 1.52 meters. And we're going to divide it by t, which we have solved for, to be 0.495 seconds. Let's see what we get. And we'll get an answer of 3.07 meters per second. Chapter 4, problem 24. In the 1991 World Track and Field Championship in Tokyo, Mike Powell jumped 8.95 meters, breaking by a full 5 centimeters the 23-year long jump record set by Bob Beamon. Assume that Powell's speed on takeoff was 9.5 meters per second, about equal to that of a sprinter, and that g, 9.8 meters per second square in Tokyo. How much less was Powell range than the maximum possible range for a particle launched at the same speed? So when they say maximum possible range, we know that the angle theta for the max is equal to 45 degrees. So knowing that, we're going to use the range formula, R to equal V squared sine 2 theta over G. So R is going to equal, they gave us a velocity of 9.5 meters per second. That's squared times the sine Theta is 45, so that'll be the sine of 90, which we know is equal to 1, divided by 9.8 meters per second square, and that's going to equal 9.209 meters. That's the max. And we want to know how much less was Powell. Well, Powell jumped 8.95 meters. So that's just 9.209 minus Powell 8.95. And that's going to be 0.259 meters, and that's going to be less. A stone is projected at a cliff of height h with an initial speed of 42.0 meters per second, directed at an angle theta equals 60 degrees above the horizon. The stone strikes at a 5.50 second after launch. Find A, the height of the cliff, B, the speed of the stone just before impact at A, and C, the maximum height h reached above the ground. A, for the height of the building, we can use Y equals Y sub O plus V sub O sine theta times T minus 1/2 GT squared. So we're looking for Y, which you would call an H at this time. So we'll go Y equal Y sub O. Well, Y sub O is 0. It's at ground level. Plus V sub O, that's given to us at 42 meters per second. Sine of theta, well, theta is given to us at 60 degrees, and the time is given to us at 5.50 seconds, and then that's 1/2 times 9.8 times 5.50 squared, and that will calculate to, which equals H. Y is the same here, which is going to equal 42 times the sine of 60 times 5.5. That's going to be 200. It's going to be minus 0.5 times 9.8 times 5.5 squared. And we get, when we take that 200 from 1/2, we get 51.82 meters. That's how high the building is. Part B, and it asks the speed of the stone just before impact on A. So we want the speed of it just before it hits here on A. So, two things we need to know about projectile motion right away. The X component is independent of the Y component. So since they're independent, we're going to have to use Pythagorean theorem to figure out what the velocity is. So we're going to have a Vx component and a Vy component. Let's do the Vx first. The thing about Vx, it moves at a constant rate the whole time it's up under the projectile, this parabolic projectile motion. It moves at a constant speed. So we can say x is equal to v sub o cosine of theta times the time to get the time, the distance from here to just up under where that projectile would have hit if it was on the ground. From here to just up to this point. So x is going to equal 42 meters per second, which was given to us, times the cosine of 60 degrees, which was also given, times 5.5 seconds, which was also given in the problem. And when you do that, that's going to be 115.5 meters. 115.5 meters is the distance from, and we know the time. The time is 5.5 seconds. So v of x, the velocity for that, is going to equal d divided by t, distance divided by t, which is 115.5 meters divided by 5.50 seconds, and that's going to equal 21 meters. Okay, so that's the v of x component. Now the v of y, we need a v of y. And what we're going to do, we're going to do a derivative on dy dt with respect to time on our y sub o plus v sub o sine t minus 1/2 gt squared with respect to time. We know when we, and this is v sub y, I know my x, y looks like an x. So v sub y, this is going to equal, well, y sub o was a constant, so that's just going to give you 0. And it's with respect to time. So sine of theta with respect to time will give us a plus v sub o sine theta. That's what we have left when we do the derivative on this, minus 2 times 1/2, which is just going to give us 1 gt. So that's our y component. So let's just figure out what this is going to be. V sub o is 42. Sine of 60 degrees minus 9.8 times 5.5 seconds. So we'll pause, I'll do the math. That's equal to a minus 17.53 meters. Okay, to get the magnitude now, all we have to do is do the square root to get the magnitude of V. We got V sub x equaling 21 meters squared. And here we have V sub y equal a minus 17.53 meters squared. And that's going to equal 27.335. Just 34 meters. So that's the velocity. That's part B. Okay, the maximum height reached. I'm going to introduce to you a formula that's not in this chapter for time. And you'll find it very useful, and I'll be using it on some of the other problems. T is equal to 2V times the sine of theta over G. This time is for level ground. Is for the time, if you know the V sub O, and you know theta, this is the time for the object to run along the ground from this point to this point, to where it hits. It's for level ground, not for if you're launching up on a pad. But we're imagining that it went all the way down to here. We just took this parabolic and took it on down as if it hit the ground. So now we can use this sign, and since we know this is a full from here to here, if we divide that by 2, that'll give us the time it's at its max, at its maximum height. For where T is going to get to the midpoint, we just have T equals V sub O sine theta over G, which is 42 meters per second times the sine of 60 over 9.8, which equals 42 times the sine of 60 divided by 9.8, which equal 3.71 seconds. Now we have to do to find that height is drop this time into this formula. Y is equal Y sub O plus V sub O sine theta times T minus 1/2 GT squared. Y sub O is 0 plus 42 meters per second times the sine of 60 degrees times our time to get to the midpoint, which is 3.71 seconds, minus 1/2 half times 9.8 times 3.71 seconds squared. And when we put all that in, we're going to get 66.06 meters. So this is fairly simple. If you can get the time to get to the midpoint, then all you have to do is drop it into your kinematic formula, y sub o plus v sub o sine theta times t minus 1/2 gt squared. So all you have to do is get the time, and then you can solve that problem.